All right. Now the second tool that we can use to analyze non-parametric tests is by using Wilcoxon Signed Rank test. Okay. Now I'm going to pause here for a while. If you forgot the guideline, okay, you can read through the guideline on how to actually carry out the Wilcoxon Signed Rank test. Okay. All right. Now let's read through the example here. Oh yeah. Now before we begin, I'm going to, as I mentioned before, I'm going to give you time to go through the guideline. All right. Now I'm going to. All right. Just to show you again the guideline on how to use Wilcoxon sign rank test. So step one, identify your hypothesis statements. Step two is to evaluate all the deviation and produce the absolute deviation, and then we are trying to ignore all zeros, and then create a ranking for all the absolute values, and then thereafter we're going to sum up all the positive ranking, and then sum up all the negative ranking, assign them as W plus and W minus. For checking purpose, the sum of the W plus and W minus must be equal to the summations of arithmetic sequence n divided by 2, n plus 1. Right. Now, third step will be to identify or choose the test statistics. Usually, that will be the smaller value between the sum of the positive rank and the sum of negative rank. And then finally, step number 4, how do we interpret our test statistics? We have to compare that with the critical um, value that we can obtain from the data booklet. And then if the critical value is greater than the test statistics value, then therefore we have sufficient evidence to reject the null hypothesis. Right? Now I hope that is clear. Use this as a reference. All right. After you've gone through the guideline, we are ready to read through this question and then try to carry out the Wilcoxon sign rank test. Right. Now, it's the same example that we did in our previous section using sign test. This is on the questions about the house Martin. Right. Now we are using the same samples here. Right. Now the record shows that several years the median number per day has been 270.5 here. So instead of using sign test this time, we're going to use Wilcoxon sign rank test to examine a 5% significant level whether there has been an increase in the number of house martin flying over the headland during the migration season of this year. Now, in the previous example, we have already tested out this, and then we found that yes, there has been an increase. Right? Now, by using Wilcoxon, let's see whether we are able to obtain the same conclusions or not. Right? Now, as usual, before we start, we must state our null hypothesis and alternative hypothesis. So our null hypothesis would be, we will say that the the median number of days, okay, median numbers per day has been, okay, I just copied directly so that you don't have to spend too much time on thinking of how to phrase this. 270.5 species, right? And then the alternative would be median number per day is greater. I think we are testing increase. Yeah, correct. So it's greater than 270.5. All right. Now I hope that is clear. Okay. Now next, instead of using binomial distributions now, okay, we're going to follow the Wilcoxon guideline. So the first step is to obtain the deviation. Okay, now if you can look at from the table here. Oh, oops, I think I used the wrong example here. It's supposed to be a house Martin. Hold on, let me get the correct numbers. It should be this one here. Yeah, is it? No. Okay. Give you a while. Did I get that correct? Yeah, here. This is the data for the house martin birds. All right. Okay. Now the first step is to obtain the deviation. Okay, so H represent number of house martins flying over a headland per day. So we are going to calculate the deviation relative to the median 270.5 there. Okay. So from here you can actually obtain all the deviations here, for instance. All right, shouldn't be a problem. Okay. Now next, we're going to obtain the absolute deviation on this without taking into account the sign itself. All right. And then after that, we're going to rank this. Yeah, we're going to rank all this based on the number. Most probably 0.5 will be rank number 1 then. Okay, so let's see whether that's true. Yep, so you have all the rank there. But of course, in the exam, you have to do it manually on your own. Okay. Now, after that, we are going to partition. In my notes, I did mention partitioning the ranking based on the deviation, not based on the absolute deviation, but based on the deviation itself, whether it's having a positive or negative. If it's negative, then we're going to write it down here. For instance, a 4, rank number 4 has a positive deviation, so I'm going to write it down here. Rank number 6 has a negative deviation, so I'm going to write it down here instead. All right, let me show you the ranking itself. You can see that 6, and then you're going to proceed on with the rest of the individual ranking based on their deviation itself. Okay, so there you have it. That's how we partition or separate the ranking that is above the median and then below the median there. All right, now I hope that is clear. All right. Now after that, of course, you are going to sum up all the positive ranking. Now in this case, the positive ranking gives us 105, whereby the negative ranking is 15. So here I'm going to write that down. The result that we have obtained is W plus the sum of the positive ranking is 105, whereby the negative ranking is 15 there. All right, now don't forget the next step is to check whether we got the ranking correct. Now to check this negative here is actually 120. Okay, we know that. We can use the arithmetic sequence here, okay, which is n divided by 2. So we have 15. Okay, 15 sets of data here. 15 plus 1. So therefore that yield 120. Yes, it does tally. So we got the ranking correct at this point. Okay. Now next, our test statistic. So the test statistics, we have to choose between the W plus and the W negative, the smaller version of the sum of rank. So the smaller value will be 15. So therefore, our test statistics will be 15 here. All right. Now, knowing that the sample size, don't forget the sample size is 15. Okay, the sample size is 15, and then the significant level is 5%. And then this is one tail test. Now, therefore, we are ready to obtain the critical value from the data booklet. All right, now let me open. Okay, this is our data booklet. Let's see what we are looking at. Okay, we are looking at Wilcoxon Signed Rank test. Okay, so from here, the table is given here. We are going to use this table to extract the critical value. How are we going to read this table? All right, very simple. All we need to do is we have to ensure we have the sample size, which is 15. So we're going to go to 15 here. Don't forget, this table has a limitations. It can only give you result up to 20. So you have sample size more than 20, you might have to use a normal approximation, right? So 15, and then is a single tail test, one tail test. Alpha is 5% significant level, one tail test. Therefore, you found that the critical, so from the data booklet, the critical value is 30 here. And then we know that this critical value is much more greater than the test statistics. Therefore, we have sufficient evidence to reject. So reject H null. So rejecting H null, meaning that the median number of house martins per day flying over the headland has already increased, and then it's greater than 270.5. All right, it's the same conclusions that we have obtained by using sign test. All right, now I hope that is clear at this point. All right, we're going to move on to second example shortly. All right, our second example, which is also the same as our previous example on the vacuum cleaner. Right? So you can read that through one more time. The median time is given as 27.35 minutes before the battery run out. And then this is a 9 sets of data that the researcher has collected. Now, instead of carrying out sign test, we have to carry out the Wilcoxon signed rank test, okay, at 5% significant level to see whether there has been any change in the average cleaning time. Okay, so we have to write down our null hypothesis and our alternative hypothesis. We will say that the whether there has been a change in the average cleaning time. So we'll say that the average cleaning time still remain the same as 27.35 minutes. Whereas our alternative will say that the average um, cleaning time is different than 27.35 minutes. Okay, so I hope that is clear. All right, so once we are done with this, as usual, we will have to perform the procedures by using Wilcoxon Signed Rank test. Right now, before that, um, just to check on all the informations given, we have a sample size of a 9. So just to check, we have 9 sets of data, and then the alpha is set at 5%. Okay, so now we are ready. We're going to calculate or determine the deviation first, as usual. Deviation here, and then you're going to calculate each individual deviation. From here, we're going to determine the absolute value for this deviation. Now, from there onwards, we're going to rank. We're going to produce the ranking based on the absolute deviation. So we're going to rank them. Okay. And then after that, we're going to isolate the positive ranking based on the deviations. So this is the result that we have obtained. Okay. So from here, I can write down my sum of rank. Positive rank is equal to 34. My sum of negative rank is equal to 11 there. Okay, now from here, my test statistic. So my test statistics will be the minimum between these two. So test statistics, I'll try to write down the minimum between W plus and W minus, which happens to be 11 in this case. Right. So once you are ready, all you need to do is refer to the data booklet to obtain the critical value. Okay, let's look at the same data booklet here. Okay, what we are looking at here would be okay, we are looking at a test statistics with a sample size of 9. So we go to sample size of 9. Right. This is difference. So difference is the two-tail test. So it's a two-tail test. at 5%. Okay, two-tailed test at 5%. So we still have to refer to 5% here. Now the critical value is a 5. And then this critical value is much lesser than the test statistic. Okay, so therefore we don't have sufficient evidence to reject null hypothesis. Instead, we're going to accept null hypothesis. By accepting null hypothesis, we will say that the average cleaning time still remain as 27.35 minutes there. All right. So I hope that that is clear for example number 2. Right now, we're going to move on to the next question shortly. All right, welcome back. Example 3, we're still with Wilcoxon Signed Rank test. Okay, now you might have questions that look something like this. There's a questionnaire is asking only 12 people, too small a sample. All right, now of course, this is situations that require a non-parametric test. All right, now do you think that asking 12 people about the new shopping center gave too small sample in the circumstances? Yes, of course, in general. That's the reason why we need to use the non-parametric test. The responses people gave about the shopping center are represented by numerical rating. Okay, you can see that. Where having no opinion equates to 4, the median value. Okay. Now and then having 1, okay, 2, 3 would be greater than or less than the 4 there. So a quick eyeball test shows that. Okay, you can see that a quick eyeball test, what does it show here? It actually shows that roughly there will be like 50% of the responses um, sort of have uh, more or less the same opinion, right? Maybe 50% of them will be having an opinion greater than the 4, another 50% will be less than 4. That is just a very quick um, outlook of the responses. But um, how would the result look like if you are going to carry out the non-parametric test at 5% significant level using Wilcoxon Signed Rank test? Okay, so the test here is we're going to test at 5% significant level whether the median is actually less than 4. All right, now let's try to determine the hypothesis statement first. All right, so we will say that the median is still 4, whereby our alternative hypothesis would be median is less than a 4 here. All right, it's less than a 4 here, right? So the next step for Wilcoxon Signed Rank test is very typical. All you need to do is obtain the deviation. So you can see that there's a deviation, and then I'll obtain the absolute deviation. Okay, so from here, this is where the ranking come in. Okay, but you notice that there's a lot of redundant in your absolute deviations. So there's a lots of redundancy with respect to the absolute deviation. So therefore, ranking become very challenging. If I were to rank this from top to bottom style, I would say that this one actually ranked number 1. This one number 2. This one number 3. Then this one will be number 4. Oh, oops, let me use a different color to differentiate that. So this is number 4, number 5, number 6, and number 7. And then lastly, I would say that number 8, number 9, and number 10 there. Right. Okay. Now you do not notice that they are like 1, 2, 3 sets with the absolute deviation of 1. So how can I determine their ranking? So for rating, rating minus 4 absolute equal to a 1 here. So I'll try to determine the ranking for this. How to do that? All I need to do is just take 1 because it has a ranking 1, 2, and 3. We're going to take the average for this. If you found that there's a redundant in the absolute deviation, then we have to obtain the average ranking. So from here, you will get a 2, which is stated here. Right now, that's how we get the ranking. So if the absolute deviations set has 1 here, having a ranking 2, then all the rest that has the same absolute deviation will have the same ranking as 2 here. Okay, so in this case, I'm going to key in manually here. So you will know that this one will be 2, then this one will also be 2 here. Yeah. Okay, now I hope that is clear. And then next for the second ranking, you notice that 4, 5, 6, and 7. Okay. So for rating deviation of 2, so the ranking is calculated using the average value for all the sum of rank. So there is a 6 and 7 divided by 4 here. All right, so that would typically be 5.5. Okay, so that will be 5.5. Just let me check if that is actually 5.5. All right, so sometime I might accidentally get the wrong number. So 22 divided by 4 here. Yep, correct. So that is actually 5.5. So all the absolute deviations that come with 2 would have a ranking of 5.5. So this is 5.5, this is 5.5, and then this is 5.5, and then lastly we have 5.5 here. And then you're going to repeat the same procedure for the last one. So for ranking, for the last ranking with deviations of a 3, the rank will be, in this case, it will be 8 plus 9 plus 10 divided by 3, which is a 9. Therefore, the ranking for all these will be a 9, 9, and a 9 here. And after that, we're going to proceed on by partitioning, separating all the rank above and below. So we're going to go through the same procedure again. This is what we have. Okay, and then by summing up the ranking, we found out that this is what we have. Okay, I'm going to write it down on top here. Sorry for the organization. Right, so the W plus, the sum of rank of sum of positive rank is equal to 9.5. Sum of negative rank is 45.5 here. All right. Okay. I hope that is clear. That's how we perform average ranking if there is a redundant absolute deviation. Okay. So from here onward, it will be a very standard procedure under our test statistic. So under our test statistics, we will choose T be the smaller version, which is 9.5 in this case. And then after that, don't forget we have a sample size of how many do we have? We have 12 here. Okay, sample size of 12. But yeah, I forgot to mention there. This is very important. I almost forgot that. For the absolute deviation of 0, we ignore that. So we don't actually include this. Therefore, the sample size supposed to be a 10 instead of a 12. So that should be a 10. And then we are testing it at a 5% significant level. So now it's time for us to refer to our data booklet. Okay, booklet. Okay, let's see what the data booklet said. Okay, so from here, this is a data booklet. All right, now we're going to check. This is a one tail test, so it's a one tail test. Okay, maybe I'll try to scroll down a bit. So this is a one tail test at 5%. Okay, at 5%, sample size is a 10. So at 5% sample size is a 10. Therefore, the critical the critical value for t is 10. Critical value for t is 10. So just let me mark that down. Therefore, the critical value is a 10. We know that this one is much more bigger than the test statistic 9.5. Therefore, we have sufficient evidence to reject the null hypothesis. So rejecting the null hypothesis, conclude that the median is actually less than 4. All right. Now that's how we carry out Wilcoxon Signed Rank test. All right. Now I hope that's been useful. Okay. Now I'm going to show you the next question shortly. All right. Question number 4. All right. Now the median weight of yam roots of a particular variety using the standard fertilizer is 5.6. Now the weight in kg of random sample of 30 roots of this variety grown using a new types of fertilizer are given below here. Now carry out a Wilcoxon test at a 10% significant level to investigate whether the roots grown with this fertilizer are on average heavier than those grown with the usual one. All right, now that is the key questions here. So we're going to write down our null hypothesis as usual. So we will say that the the median weight the median weight of yam roots um, is 5.6 kg using standard fertilizer, right? And then the median weight of yam roots. Okay, to investigate whether roots grown with this fertilizer are on average heavier. Okay, so median weight of yam roots using new fertilizer. The median weight of yam root using the new fertilizer remain the same. So we make assumptions that for the alternative, the median weight of yam root using new fertilizer is greater than 5.6 kg. Okay, so there you have it. That's our hypothesis statement. All right, so now we are ready to go through the same procedures for Wilcoxon. That will be, we have to obtain the deviation. So obtaining the deviations for this shouldn't be a problem, but there are lots of data involved here. Okay, all right. Now next we're going to obtain the absolute. So you can see that there's an absolute deviation. Next we're going to rank them. Yeah, of course you're going to rank them as usual. And then after that, partitions the positive rank and then the negative rank. All right, so from here we should be able to obtain the sum of positive rank. So we're going to write down the sum of positive rank. So the sum of positive rank is 314. So we'll write down 314. And then the sum of negative rank is 151 here. Okay, so that's what we are having at this point of time. Okay, all right. So next, our test statistics. So don't forget test statistic. Test statistics will be the smaller versions between the W here. That will be 151. Okay, 151. Right. Now the next one will be we're going to refer to the our data booklet. Okay, as usual, after we've done this, we're going to refer to our data booklet. Uh, Knowing that the significant level is 10%, this is a single tail test. Sample size is 30, so n is equal to 30. Right. So we are going to refer to the data booklet now. Okay, and then we found that, oops, there is no 30 here. The maximum sample size allowed in the table is only up to 20. But luckily, they do give us a suggestion for large value of n. Okay, for any value greater than 20. Now, each p and q can be approximated by normal distributions with the mean this and this. So therefore, I'm going to calculate the mean in this case. So the mean can be estimated using a quarter of n. The n is 30 here, 31 here. All right. Okay, so by using the calculator, just let me quickly check that out. By 31 there, so that would give me 232.5. And then after that, I need to calculate the variance itself. So the variance, yep. So the variance. Oh yeah, this is the mean. I might as well use the standard symbol instead of x bar. Okay, so the variance is given by 30 divided by 24, 31. Okay, and then after that 61 here. So that would be a very huge number then, I think. Okay, just let me try that out. Okay. All right. Now that would be a very huge number, 2,363.75. Okay. And then from here, I will need to determine the rejection region. The rejection region is stated as 10%. Stated as 10%. Right? So my test statistics that I'm supposed to calculate here would be, I'm supposed to calculate my test statistics that is less than 151. So the probability of less than 151 there. Of course, in general, you have to use your data booklet and then go through the normal calculations on getting the z-score. So I just roughly show it to you here. That is pz less than 151 minus of 232.5 divided by 2363.75 square root. All right. Now that's how we get the probability. Okay. Now if you actually calculate that, all right. Now let me get my calculator here. So this is a normal distribution. Okay. The mean is 232.5. The standard deviation is square root again. Square root of 2363.75. All right, and then I'm interested to get anything on the left hand side, anything less than 151. Okay, anything less than 151. Okay, now don't forget that I have made one mistake here, right? Because whenever we approximate, we are actually converting the discrete value into continuous value. So don't forget to make the continuity correction. Yeah, that's what I mean. So the continuity corrections that need to be performed will be here. So that will be 151.5 here. So I should actually include 151.5. Therefore here should also be 0.5 here, right? Then you'll be able to obtain the value correctly. Okay, now let me rewrite the correction. This is need to be need to carry out continuity correction. Therefore, the correct calculations to carry out will be this one here. T must be less than 151.5 here. And then from your data booklet, you should be able to get this answer here. So I'm going to use this one here. You should be able to get, hold on, I think it's 0.5 there. Yep. So you should be able to get 0.0479. Right now, the data booklet part, I will leave it to you to refer to. But you should be able to get 0.0479. Okay, and then 0.047479 actually fall within the rejection region there. Okay, it actually fall within the rejection region because the rejection region is 10%. Okay, because the rejection region is 10%, this is actually smaller than 10%. Therefore, we have sufficient evidence to reject. So the rejection zone is 10%. Somewhere here, for instance, this is actually 10%. All right. So therefore, we have sufficient evidence to reject null hypothesis. So as a conclusion, the medium weight of yam roots using new fertilizer is greater than 5.6 kilogram. All right. Now I hope that is clear at this point. All right. I'm going to move on to the next section shortly. Right. Example number 5. All right. Here we need to determine the 1% one tail test critical value for a sample size of 84 here. So the n is equal to 84. Right. Now the critical value that we are talking about will be the test statistical value. Therefore, it must satisfy this inequality because it is 1% one tail test. So it must be less than 0.01 here. Now, is the formula always standard? Yes. In this case, it's always less than 0.01 here. Right? So we are supposed to determine the value for t here. Right? Now, don't forget, because we are converting the discrete into the continuous, so therefore there must be continuity correction. Therefore, usually we will write it down as t less than t plus 0.5 here. Okay, so I hope that's clear. And then from here, we need to approximate it using normal distribution. Okay, now the mean is actually given by a quarter, 84 or quarter, 85 there. So that is actually 21. So just let me try to tabulate this properly. So we have by the 85 here. So we have 1785. And then as for the variance, that will be 84 over 24 here by 85. And then by what do we have here? 169? Yeah, 169. So therefore, this value is much more larger. If you actually calculate this properly, you should be able to obtain, let me check, as 50277.5. Okay. So from here, we can apply the z-score. So from this equation here, that will be the same as t plus 0.5 minus of 1785 divided by 50277.5 square root, and then that should be less than 0.01. Okay, so I hope that is clear. Right, now from here onward, we need to look at the data booklet for normal distributions. 0.01, so area of 0.01. So where is that area 0.01? The area of 0.01 is the same as 0.99 based on this shading here. Okay, so I'm looking for 0.99. So where is that 0.99? Let me see. So I can get for close approximations. Okay, maybe it will be okay. If you want to get the exact one, it should be okay. Let me check. Okay, if you want to get the exact one, it will be this. It will be 2.3, 2.312, 2.312, and then 1, 2, 3, 4, 5, 6, 6. So which means t plus 0.5 minus 1785 divided by 50277.5. Okay, so this value here must be less than, all right. Okay, this value must be less than 2.326. Okay, because it's on the left hand tail, so it should be less than negative 2.326. And then from here, just let me try out, and then let's see what is the value for this one here. So if you do it this way, it will be 502. Okay, 50277.5. Okay, cool. And then that will be 2.326. Okay, so that will be hold on, plus oops, this is subtract here 1785. Okay, so subtract here plus, so there will be 1 point, and then finally we have 0.5. So the final answer will be t will be less than 1.263. 1.263, right? So I hope that is clear at this point. All right, I think I made a mistake with my numbers there. The correct one should be 2000. I think I made a mistake here. That's actually hold on, let me see, it's 2300. Yeah, 2326. So the correct one should be 2326. 2326 there, right? And then therefore this number here should be 1262.95 to be precise. So therefore we will say that the critical region is anything less than, so the critical region will refer to the critical value anything less than 12662, right? Equal to less than or equal to 12662 in this case, right? Now I hope that is clear with this calculation, right? Now next I'm going to move on with another applications of Wilcoxon Signed Rank test.